Well, welcome to my lecture on continuous distributions. So just one big difference for a continuous distribution is that there's a density function and let's call that density function f of x, and the density function satisfies two things. One is that the total probability, which is now calculated with an integral, is equal to 1. And the second is that there's no negative probability. F of x is greater than or equal to 0. And what this translates to is no negative probability. Okay. Now, for a density function continuous, there's some big differences. So if you want to calculate the probability x is less than or equal to a value a, that's going to be this integral from minus infinity to a of f of x dx. This is also the cumulative. This would be f of a, and that is by definition the cumulative the cumulative distribution evaluated at a. Okay. If I want to calculate the probability that x is between 2 points, this is going to be the integral from a to b of f of x dx. Okay. So how we calculate probabilities is no longer with a sum, it's with a very fancy sum, which is the integral. Because after all, the integral is defined as an infinite summation, a Riemann sum, right? Okay, so other things. If I wanted to calculate the expected value, which is the average, well, that's going to be this integral from minus infinity to infinity of x times f of x dx. Similarly, e of x squared, the second moment, is going to be, instead of x, is going to be x squared f of x dx. And more generally, if I have a function g of x, I can take its expected value by doing this. It will be g of x times f of x dx. And just a few more things. The moment generating function, that is an expected value of a function, e to the t times x. And this is going to be this integral from minus infinity to infinity of e to the t times x times f of x dx. Okay. One thing that I should say is that commonly, so often, we don't need these limits because f of x might be defined on a smaller interval. It's still correct to write minus infinity to infinity, though. Okay. But in computation, it will be different. So here's just a quick example. So consider the arrival time of a handyman. And maybe the handyman is coming from Home Depot, and you're told that, hey, this handy person is going to arrive between 8 and noon, which is between 8 a.m. and noon. Okay. And you're told no one time is more likely. So that is, if I made a histogram of x, which is the arrival time, and p of x, it should look like that. It's just a flat line. So probability is constant. So i.e. p of x is constant. And the arrival time is between 8 and 12. So let me move that x so it's out of the way. Okay. So what you're being told is that f of x, that's the density, is going to be a constant if it's between 8 and 12, and we're told that he's not going to arrive at any other times. Okay, so here's going to be the first thing we need to do. We need to determine the value of k that makes f of x a valid density. Okay, so let's answer that question. So we know that the total probability, 1, is equal to this integral from minus infinity to infinity of f of x dx. Well, notice that f of x is only non-zero between these values. It's only non-zero between 8 and 12. And it takes the value of k on those values. Otherwise, it has a value of 0. So when we anti-differentiate, this will be k times x from 8 to 12. And this will be k times 12 minus 8, which is 4. So k is equal to 1/4. And f of x, the density, is going to be 1/4 and 0. This is if it's between 8, x, and 12. And it's 0 else. Okay. Well, second, let's calculate a probability. Calculate the probability the handyman arrives between 9 and 11. Okay, so first, let's declare the random variable. Let x be the arrival time of the handyman. Then p of x is, probability x is between 9 and 11 is equal to this integral from 9 to 11 of 1/4 dx. After all, 1/4 is the value of k, so that is our density function. So this will be 1/4 times x evaluated from 9 to 11, which is going to be 1/4 times 11 minus 9, and that's 1/2. So it's a 50% chance. Okay. If I was to look at this, here's going to be f of x, here's going to be x, here's going to be 8, here's going to be 12, and that's 1/4. Okay. I want to calculate that between 9 and 11. So remember, the integral computes this area, and this is a 1/2 probability. Which is the same as the area. Now, someone might ask you, hey, notice I get the same answer if I do, well, it doesn't matter if I do this, that's equal to 1/2, or if I do the less than or equal to. And that's because the area, the difference between that is a line. Okay, so probability x is equal to 9 exactly is equal to 0. And if I had to prove that, the proof would go like this. Okay, probability x is equal to 9 is equal to, well, that means x is bigger than or equal to 9 and also less than or equal to 9, which is the integral from 9 to 9 of f of x dx, and that has no area. So that's going to be f of 9 minus f of 9, and that's 0. Okay. Probability of a point is 0, is what we just showed. When, and this is really important because it's not true if it's discrete, when x is continuous. Okay. Now, what if I was asked to compute the average waiting time, e of x? Well, this would be the integral from minus infinity to infinity of x times f of x. And this will be, well, I don't have to integrate from minus infinity to infinity. Instead, I can integrate from 8 to 12 of x times 1/4 dx. And this value will be 1/8 times x squared evaluated at 8 and 12, which is going to be 12 squared minus 8 squared over 8. Okay, that's our average value. Okay, now what if I want to calculate this? What if I want to calculate the moment generating function? I could do that. That would be the expected value of e to the t times x. And this will be this integral from minus infinity to infinity of e to the t times x times f of x. But remember, I know that f of x only takes on values between 8 and 12 of e to the t times x over 1/4 dx. So this simply anti-differentiates to e to the t times x divided by t over 4 from 8 to 12. So this will be e to the 12t minus e to the 4t divided by 4t right there. And that is the moment generating function in this case. Okay. Well, let's do one more example here. Let f of x equal to kx if x is between 0 and 1. Okay. So here's our first question. What value of k makes f of x a valid density? And if I was to answer this question, we'd do it the same way we did it before. 1 is the total probability, and that would be the integral from minus infinity to infinity of f of x dx. But I don't have to integrate from minus infinity to infinity. It's only non-zero from 0 to 1 of k times x dx. So 1 is equal to that antiderivative, which is k times x squared over 2 evaluated at 0 and 1. So when we do that evaluation, k is going to be equal to 2. Okay. So the density is f of x equals 2x if 0x is less than 1 and it's 0 else. Okay. So here's our second question, B. Calculate the probability that x is between 1/2 and 3/4. Well, if I was to calculate this probability, I just need to calculate an integral. It's the integral from 1/2 to 3/4 of 2 times x dx, which is x squared evaluated at 3/4 and 1/2. So when we evaluate that, we'll get 3/4 squared minus 1/2 squared, and that's going to be equal to 9/16 minus 1/4. Okay, so of course that's going to be 5/16. Okay, now here's another question we could ask. Calculate e of x. And e of x is this integral of x times f of x dx from minus infinity to infinity. Well, I'm going to calculate minus infinity. Instead of having minus infinity, I'll have 0 to 1 of x times 2x dx. And that's going to be 2/3 times x cubed, evaluated at 0, 1, which is just 2/3. What if I asked you to calculate the variance of x? So that's second and third is to calculate variance of x. Variance of x is going to be e of x squared minus mu squared. And this was mu. Mu is e of x. So I'm going to have minus 2/3 squared, and I need to calculate e of x squared. E of x squared is going to be this integral from minus infinity to infinity of x squared times f of x dx, which is going to be integral from 0 to 1 of x squared times 2x dx. And when we anti-differentiate 0 to 1 of 2x cubed dx, that's going to be 1/2 times x to the 4th, evaluated at 0 and 1, which is just 1/2. So this is going to be 1/2, and we calculated our variance. Our variance is this quantity. That's a 3. okay? So we calculated variance, and finally, for the last thing I'd like to calculate the moment generating function, mx of t. And that's defined to be the expected value of e to the t times x, which is this integral from minus infinity to infinity of e to the t times x times f of x dx, which is this integral from f of x takes on values from 0 to 1, e to the t times x times 2x dx, which is twice this integral from 0 to 1 of x times e to the t times x dx. And in order to anti-differentiate this, we need to integrate by parts. So just remember the integral of u times v prime is equal to u times v minus this integral of u times v prime. Okay, so I'm going to select, small little error there, u prime v here, and I'll put that in red because that's a big boo-boo. So I'm going to let u equal to x, so u prime is equal to 1. And v prime then has to be equal to e to the t times x. And the antiderivative of this is with respect to x. So v is equal to e to the t times x over x. Over t. Okay, and now we're ready to calculate the moment generating function. Okay, so it's going to be twice this integral from 0 to 1 of x times e to the t times x dx. We apply integration by parts, and this becomes twice. This will be x times e to the t times x over t evaluated at 0, 1 minus this integral from 0 to 1. X becomes the value 1, so I just won't even write it. E to the t times x over t dx. Okay. Now, when we evaluate this, we'll see that this will be 2 times, well, when x is 1, we'll have e to the t over t. When x is 0, everything is 0. So minus 0 minus this antiderivative. This will be e to the t times x over t squared evaluated at 0 and 1. And then finally, we'll see this will be e to the t over t minus, well, when x is 1, this will be e to the t over t squared minus a double negative makes it a plus. When x is 0, we'll get 1 over t squared. Okay, and that's our moment generating function. Okay, so this beautiful thing right here, that's our moment generating function. And that was it for our introduction to continuous random variables. Next time I'm going to talk about the Poisson and the gamma distributions along with the function. Okay, thank you very much.